Welcome everyone to the last ITC Luncheon of the spring semester. So the spring is all around us, and we're headed to the summer. We just had an excellent ITC colloquium by Dimitri he already spoke at the lunch, so he will not speak today. We have a first speaker who just won the annual Keto Prize, named after Eric Keto, a senior member of the ITC that contributed to establish this prize. This prize is awarded once a year for the best PhD thesis in theoretical astrophysics at Harvard. And this year, Philip Mocz, who is standing over there, was selected to receive that prize, and we will have the ceremony at 2 p.m. But as a new tradition, we invite the recipient to give one of the ITC lunch presentations. And I also wanted to ask Eric to say a few words at lunch. Perhaps he will do it now, and then I'll follow with the rest of the speakers.
And so, like Avi said, this prize is awarded to the graduate student in theoretical astrophysics whose thesis is selected as the best by the senior members of the ITC, which includes the SAO staff and Harvard faculty. This prize was established about 10 years ago by the ITC to encourage excellence in theoretical astrophysics. And since the prize was endowed by myself, I have the privilege of presenting the award, but the selection, like I said, is made by the ITC. And this year's recipient is Philip Mocz, and congratulations. And Philip is particularly recognized for his contributions in numerical methods, among them themes for incorporating magnetohydrodynamics into moving mesh codes. And from Philip's thesis advisor, Professor Lorimer, he said that until Philip became involved with this problem, it was believed by the leading experts in the field that it would be either very difficult or impossible to perform constrained transport in a numerical hydrodynamics code that uses a moving unstructured mesh, such as the Arepo code. And through several remarkable pieces of analysis, Philip showed how constrained transport could be implemented on a moving mesh, and his tests verified that the magnetic field can be guaranteed divergence-free to machine precision. So that research was published in an article called the Constrained Transport Scheme for MHD on Unstructured Static and Moving Meshes. And then Philip invented another better method to solve the same impossible problem, which he then published as a moving mesh unstaggered constrained transport scheme for magnetohydrodynamics. So he has those two papers. And then, as Avi said, there's a prize ceremony at 2 p.m. And as most of you know, I'm going to retire from SAO, and there'll be another retirement celebration folded into that 2 p.m. And so congratulations again to Philip, and he'll tell us about his research.
Thank you, Eric. And I should mention that we have some of the mixed feelings, because we really wanted you to stay with us for many years as an active senior member, and but we are really grateful for your many contributions, and especially the generosity that in your funding of this prize. I should mention that there was a discussion about it at the senior ITC meeting, and someone suggested that we should establish a prize for the best PhD in theoretical astrophysics, and the only issue was how to get it funded. And by the end of that meeting, we had a donor. He was in the room, and his name was Eric Keto, and that was very generous of you. And so we will also celebrate Eric's contributions to the ITC at 2 p.m. Aside from Philip, we hear from Duncan Lorimer, who should be somewhere here, over there, who is visiting us from West Virginia University. And as many of you know, he is the person that discovered the first fast radio burst. By now it's one of the important frontiers in transient radio astronomy. And he will talk about the galactic population of pulsar black hole binaries. Then we'll hear from Annalisa Pillepich, that used to be here at the ITC as an ITC member, and now she's at MPIA. And she will talk about introducing the IllustrisTNG project, and we'll hear more about the T, N, and G. What do they mean? And finally, we'll hear from Sandy Yuan, who will tell us about using galaxy pairs to investigate the three-point correlation function in the squeezed limit.
Okay, thank you, Avi, and thank you, Eric. So I've given a couple of talks here before, so today I'm talking about something different, a side project, integer lattice method for solving the Vlasov-Poisson equation. This is work with applied mathematician Saru Suchi. And an outline of the talk, I'll briefly introduce Vlasov-Poisson and talk about the integer lattice technique I developed to solve the dynamics for such a problem. I'll go through some simple test problems, such as simulating Jeans instability or Landau damping. I'll talk about way we can solve for six-dimensional phase space using only 4 dimensions of memory. And finally, I'll talk about extensions of the method to weakly collisional systems and maybe plasma systems. So just a background, so Vlasov-Poisson, it's just the equations for the dynamics of collisionless self-gravitating fluids, such as cold dark matter. And you really want to evolve the 6-dimensional distribution function given by equation 1. So it's a very simple set of equations. It's really a statement of the conservation of phase space density. So F is constant along the trajectories of the system. This is known as Liouville's theorem. The complication is that this is 6-dimensional, so it's very expensive with regards to memory. So there is interest in solving for the fine-grained phase space structure of such systems because it has multiple applications to modeling redshift space distortion, kinetic Sunyaev, Zeldovich effect, shell crossing, etc. And typically, we use n-body simulations, which can be thought of as a Monte Carlo sampling of the phase space, but they give poor resolution in the low density regions where you actually do not sample the phase space. So another motivation for the numerical method is that when you're designing methods, it's important to preserve physical symmetries and invariance of the method. So this is just highlighting 2 different ways to solve for this orbit around a planet around a star, and it's exaggerating the numerical effects you can get based on how you discretize your system. And one thing we worry about, one thing that the integer lattice method is good at is actually obeying this Poincaré recurrence theorem for these systems, which will, after a sufficiently long but finite amount of time, return to its initial state. So this integer lattice I'll be talking about, it's a completely reversible system, and you can recover these periodic solutions to the system. So it's actually super simple, but a little bit strange when you first see it. You evolve velocities and densities according to acceleration and the velocity, but you perform this rounding to nearest integer operator, which really just restricts the motion to a lattice. So your acceleration A is obtained just from a Poisson solver, and depending on your lattice spacing, you can actually get much better than machine precision localization of particles. Although in practice that might only be relevant for sparse systems. So a better way to see it is pictorially. So really your phase space distribution function F lives on this lattice, and then first you receive a kick from the Poisson solver, which can push so this is just in one spatial dimension, two phase space dimensions. So you receive the kick from the Poisson solver, you shift the particles up and down, and then you receive a drift from the kinetic term, which is just a shearing motion, very simple. So to summarize, each step is just a very simple permutation of lattice sites. There is no round-off error, so you don't get a random Poisson error in your last few digits of your location because everything's restricted to lattice sites. It's completely reversible, conservative, fully Lagrangian, and I can show that this system has a Hamiltonian that approaches the Hamiltonian of the continuous system in the limit that resolution is increased. And one interesting side effect of this method is that every single orbit is periodic. So in a sense, chaos, true chaos disappears, but there's an analogy which is extremely long period orbits. But every single orbit, so every single particle will return to its original position at some point in the system. And you can study chaos, for example, by looking at the distribution of long period orbits. Okay, so just some tests. This is a gene's instability test in one dimension. So there's a Gaussian-like initial profile along the velocity direction, and you see a gene's unstable mode. Things collapse, and you get a complicated spiral looking like phase space structure, like here. And I just want to visually compare with using different techniques. So on the left is the integer lattice technique compared with the particle mesh technique, which has Monte Carlo noise. So a different noise property than the integer lattice technique. And finally, you can use 6-dimensional finite volume schemes, and this usually has diffusion. So you can see that many of the fine grained structure is actually erased in this final method. And this is another interesting test, the Landau damping test, where you start out with a Gaussian profile in both dimensions, and it's close to a smooth equilibrium solution, but not quite. So you end up winding up these spiral arms and get these very thin structures. So it closely approximates a smooth equilibrium, but can never reach it. And here's just a comparison using n-body techniques with integer lattice technique and finite volume. And what actually happens with finite volume schemes is that you have numerical diffusion, so you actually diffuse and erase these thin arms, and then you actually reach the equilibrium technique. So you go steady state, which is not true for the n-body and the integer lattice technique. And so there's actually a way to, so a real advantage of this method over n-body techniques is that you can reduce the memory requirement down to 4 dimensions, but increase the computational time by a factor of n. So n roughly scales as the number of spatial dimensions, number of velocity dimensions, and also the number of time steps in your simulation. So 60 phase space, you require order n to the 6 storage space in memory, but since integer lattice has this property of being exactly reversible, you can always just store the accelerations at each time step. There's n cubed of them, and then there's nt time steps. So you get n-fourth integers you need to store. And by increasing the computational complexity by a factor of n, you can always recover everything back to the initial condition exactly, and going both forwards and backwards. So just wanted to highlight a couple of applications of the method. There's you can add in a weakly collisional term. So to look at the structure of weakly collisional shocks, typically people use direct simulation Monte Carlo methods. This is a new alternative. So here is a shock structure, just comparing it by reducing the amount of collision, and in the background you can see the true solution for fluid equations and how the weakly collisional shock deviates from that. So this is actually relevant for astrophysics when you want to model something like ground pressure stripping, something I hope to do in the future with this method. So this is actually in the weakly collisional regime because the mean free path of particles is roughly the length scale of the galaxy. So it's not true fluid equation approximation here. And finally, you can simulate plasma systems as well. Vlasov-Maxwell equations look very similar to Vlasov-Poisson equations, just with opposite sign. So this is just a simulation of the mixing of two-stream instability here. So that really concludes my talk. So the integer lattice method is very simple, very fast, efficient method to study 6-dimensional Vlasov-Poisson systems. And the numerical method has nice properties that are unique to the method, such as reversibility and no round-off error, and obeying Poincaré's recurrence relation. And finally, there's a memory-efficient implementation that could really open the doors to simulating 6D phase space in the near future. Okay, thank you.
For the lattice, in principle, makes it very natural for describing quantum systems that where phase space is discretized by h bar. So could you comment on how useful that might be?
Yeah, so I think that, so I have to think about more how, yes, okay, so So I think it's not as directly related as you might think, but there might be ways to incorporate the effect of an H-bar onto a lattice. But in theory, this is just trying to approximate a very classical system. I don't think you'll get quantum-like effects or anything like that.
It's very amenable to compression, right? The fact that it's on an integer lattice. In principle, you could apply sort of like a gzip or something on the time snapshot to even conserve more memory. Have you looked into doing that? Apparently, that's what's done for things like massive game of life simulations.
Yeah, exactly. So that's actually my my plan to reduce the memory down to order n cubed, actually. So rather than tracing back to the initial condition every time, if you can run your simulation up to a certain point and then create a compressed version of the simulation at that point, then you can always just trace back to a later time in the simulation and really, really save on memory. So there's a lot of people actually in the computer science departments right now working on compression for just this type of data that I'm in communication with. So we hope to do something like that. Okay.
All right. Well, very good afternoon to everyone. It's a pleasure to be back in this hallowed auditorium. My name is Duncan Lorimer. I'm from West Virginia University. I'm going to tell you a little bit today. It's just a beginnings of a project that I hope it's been on my mind for a while, but I hope we'll get some more substantive results to show you. But I've got some interesting things to talk about. So for a long time, people have been interested in the population of pulsar black hole binaries. So we heard a very nice talk this morning about the supermassive black hole at the Galactic Center, and pulsars around that will be fantastic for many reasons. But it'll also be very interesting if we can find even one pulsar going around a black hole, a stellar mass black hole in the Milky Way. And here's a nice little diagram by Michael Kramer about that shows pictorially what we're interested in. Over the years, people have done population syntheses about these, and the sort of standard rule of thumb is that you find one of these pulsar black hole binaries for every 1,000 pulsars that you have. Right. So right now we have 2,500 radio pulsars in the Milky Way, and so the question is, have we seen one yet? And if so, what would it look like? So that's one of the things we're trying to get into in this project. So it brings in sort of three elements to it. And this is a collaboration with my current undergraduate student, Emily Steiner, who's doing much of the work at WVU. We're getting theoretical expertise on the population synthesis side from Chris Belczynski at Warsaw. And so Chris has this Star Trek code that is one of the stellar population synthesis codes out there that attempts to follow the evolution of binary stars of all different kinds and incorporates various prescriptions for the physics of mass transfer and so on. And what we're going to ultimately do is normalize the code so that it can predict a certain number of binary systems involving types of stars that we do understand, and see what it predicts in terms of pulsar black hole systems. We've kind of just let it run free at the moment. We're going to normalize that number as we go on, but you'll see what we can do already. And we're going to basically merge that population synthesis with something that's fairly well understood in the radio pulsar community. That's the detectability of radio pulsars. So we'll be using a simulation package that's freely available in the community. It's a Python-based code that models the detection of pulsars. And so, as I said, what I'm interested in are what are the observational signatures of these binary systems. So just in a very sort of nutshell guide to binary evolution, you've got a primary star and a secondary star. The primary is more massive, and it evolves off the main sequence first. It goes through a giant phase, and then depending on, and there's mass transfer at that level via Roche-Loeb overflow, and depending on the mass of the various components will depend on the outcomes down here. If the primary forms a white dwarf, then you'll get a binary system involving a white dwarf. You can get a neutron star formed or a black hole formed from that primary star, and subsequent evolution proceeds. So we have seen in the radio pulsar community many of these examples of systems down here, but the case down here where we have a neutron star black hole we have not yet seen. In this particular case, you just basically expect the pulsar just to spin down. There would be very little mass transfer, essentially zero mass transfer. The black hole is formed first, the pulsar forms second, and it's basically just spinning down as an ordinary pulsar. And Chris's code that follows these objects allows us to predict the orbital parameters of them. This is showing the orbital period of these binary pulsar black hole binaries in a logarithmic scale. So note that's the log of the period in years. So 1 year is here. So there's this bimodal population whose origin is not well known to me at the moment, but there's a short period population, and there's an extremely long period wide orbit population of pulsar black hole binaries that are in principle predicted in these simulations. And the pulsar side of things, we've known for a long time, in the words of our venerable president, that the pulsar sample is a rigged system. We're biased towards nearby bright pulsars, and so when you look at the projection of the pulsars on the XY plane, you tend to see the pulsars around close to the sun. And the number counts of pulsars fall off rapidly compared to expectations where you have no selectional effects. And we've been able to, we and many other groups now have been able to model the population, model these biases using a Monte Carlo simulation where we give the neutron stars properties and let them evolve in the galactic potential. We simulate pulsar surveys and see if their physical parameters are such that they would exceed the detection threshold, and then we compare the model sample with the true sample. We're at the stage now where we've got a pretty good understanding of the luminosity function of pulsars, and we can understand that side of things quite well. So what I'm doing at the moment is just taking some of these detectable pulsars that have putative black hole orbits around them, and then just asking the question, what would they look like in radio pulsar timing data? So for those of you who don't know, when you find a pulsar, you time it for a year or so. That means you monitor it with a radio telescope, and you attempt to measure the arrival time of the pulse and compare it with a model for how the pulse should be arriving. And that model can have orbital parameters in, and so on and so forth. And what you're looking at here are some simulated residuals, the difference between the model and the observed arrival time over a 3,000-day period. This would be rather a long data set. There aren't many pulsars that are observed for such a long time. They're being observed approximately every other week, I think, in this particular simulation. And you basically see white noise residuals here. So what we've done is we've modeled the system perfectly. We assume that we know the black hole orbit, which in this case is a 200-year orbit, and with a very, very well-known orbital separation and eccentricity. But that's not the case in the pulsars that we might have in our sample. So now then we can ask the question, well, what happens if you try to model the pulsars without taking into account the orbital parameters of the black hole? And it looks like this. You get, if you look at the residual here, it's about, the scale there is about 20 milliseconds, plus or minus 20 milliseconds. The spin period of this pulsar is 800 milliseconds. So it's well within a rotational phase of the pulsar itself. We're able to track the pulsar's spin, but you can see that it's now no longer white noise. It has this very systematic dependence, this overall sort of quartic curve and some bumps and wiggles superposed on that. And so what's happening there is that the black hole orbit is getting absorbed into the spin parameters of the pulsars, and it's just not able to model it correctly. But it is able, you are at least able to track the rotational phase of the pulse. Now, for anyone that's looked at pulsar timing residuals, and there may be some people in the audience that have seen these plots, this actually looks very familiar. We see this behavior a lot in when you observe pulsars over long periods of time. There's some examples over there. Now, I'm not saying here that all of these pulsars have black holes in orbit around them, but I'm saying here that what we're seeing just in this very early phase is an observational signature that is potentially testable in these, potentially present in the data itself. And so what we're going to do going forward is to compute a whole catalog of these pulsar timing residuals and start to confront them with the real sample. So that's really all I've got to say at this point. We're going to start moving ahead on different fronts. I want to get, as I said right at the beginning, to normalize the population synthesis using Chris's code, imposing more constraints on it and actually limiting the sample of pulsars and seeing how many of them are actually detectable. But the signatures in the residuals that we're already seeing are something that is not unfamiliar with what's already out there. So we're now interested in ways of trying to interpret that. So this is very much a work in progress. So I would certainly welcome all comments and suggestions that you have in this forum. Thanks a lot for your time. Yes, amazing.
So the way to identify a black hole, I mean, obviously there could be many binary companions that are much more numerous than black holes and plasmas, and principally the kick from the supernova is not large enough. But the distinguishing feature of the black hole is that you don't see any light coming from, and also
Right.
that the mass would be above, let's say, 3 solar masses. But the question is, in your plots, it was not obvious that you can actually infer whether the mass is about 3 solar masses.
No, not at all. Actually, yeah. These there may be some way we can measure the structure here and look at higher order frequency derivatives and see if we can make constraints on the orbit. I haven't tried that yet. That's one thing to try. The other thing that I will say, though, if you go back to this orbital period distribution, so if you start at the left-hand side here, where you've got the very tight orbits, all of these would have already been seen if any of them had been present in the pulsar sample that we have. It's really once you go beyond a period of a year, that's when we're potentially missing systems. So in some senses, you think about normalizing this distribution, it's probably going to drop down here, and this is going to be a very low bump, and we're going to be looking for exactly how many binaries are in that second population.
You can't test GR very much because it's very
No, they're not going to be very precise for that. It's more on a stellar evolution ground.
So, the guy you're working with archival data, how rich is your archive?
Oh, right. So we have we're simulating data, so that's one side of things, and then we're confronting it with the archives. And this is it's a good question. They are so this sample here, you can actually see it's a similar time span for half a dozen pulsars or so. There is something like about, out of the 2,000 pulsars, bless you, there are about 400 or 500 that are sampled to this level, something like that. But not certainly most of the pulsars that get observed, they just due to the lack of telescope time, they just get observed for a year and then they're just thrown back into the pond.
Is there any statistic of the simulated data that has been used to triage the sample? Like, what's the power spectrum of those residuals? Because the red noise of pulsars has
that's
power spectrum.
That's one of the things we want to try next. And what we might do is do local fits to the time series and look at the frequency change, the frequency derivative changes, and see if that has any signature that's different to what we see in.
Like breaking indices.
Yeah, right.
To understand the population, you had mentioned that the numbers come out of PUPs in something like 1 per 1,000 pulsars.
Mm-hmm.
Now, does that mean pulsars that you would have seen?
Yes.
Or does that mean the galactic population? So
every okay, so for every 1,000 pulsars you find that the sort of standard is one of those would be a pulsar black hole binary. In terms of pulsars in the Milky Way, it depends how you kind of define them. There's about 10 to the 5 that are active radio pulsars, whether they're beaming towards you or not. So you divide that number by a couple of hundred.
So not a whole lot.
No, but potentially much less actually.
The uncertainty, though, in the population synthesis must be rather difficult to quantify because particularly forming these closed systems comes out of physical processes that are not well understood.
That's right. Yeah.
As you can see, the difference between what was predicted prior to gravity waves and what we're seeing.
Right.
Really important difference.
Right.
Qualitative difference. And so the same thing might be the case here. So what you're doing in terms of simulating and then archival work seems like it's, in a sense, more fundamental at this point than maybe tying it to a population synthesis.
Yes, but you need the population synthesis is really useful right now in the sense that it gives us representative binary parameters to build up a catalog with. Yeah.
So, Duncan, I'm a little suspicious of Chris's double peak population in the sense that the very long period orbits would be the easiest ones to disrupt from the neutron stars and receive kicks. So it's very surprising that he's predicting.
Yeah.
Seeing that the black hole neutron star systems would block such long periods.
I agree.
Counter to where you would expect them to be.
Yeah, they are highly eccentric, so they're just clinging on. But you're right. We need to be very cognizant of what opening up the black box. So far, I'm just taking the numbers that he's giving me at face value. But yeah, that's a good point.
We should mention also that that finding transients, radio transients, is a family business for because his wife Lorimer discovered that the RX were getting radio transient around the same year. Or?
It was about 2004. Yeah.
Oh,
Yeah.
a few years before
Yeah.
you published
Right.
Fast Radio.
Yeah, and I'll be telling you that story this afternoon, if those of you who are around. Thank you.
Can you hear me? Yes? I'll have to hold this. All right. Okay. Well, good afternoon, everybody. I'm very happy to be back here to introduce you to IllustrisTNG. You heard already a talk, probably in February, by Federico Marinacci using IllustrisTNG data. Today, I take a step back to tell you what's behind it. And TNG stands for the next generation. We are not very creative in our team. And as the name is supposed to evoke, we are all building upon the successes of Illustris, which was one of the first large-scale simulation for making galaxies and evolve them from high redshift to redshift 0. The latter is depicted in this movie that I'm showing here, and that was made by Mark Focusberger just a few years ago. This is my personal tribute to the efforts and to the incredible results of my colleagues in a time where I wasn't around. And also today I am a spokesperson of a series of people. These are between Boston, New York, Heidelberg, and Munich, all captained by Volker Springel and Lars Enquist. And you may recognize some faces around. So, as a reminder, we are doing cosmological simulations for galaxy physics, so galaxy formation and evolution, meaning that we are also solving gravity and hydrodynamics of the cosmic gas. And with IllustrisTNG, as I said, we wanted to build and expand upon what obtained with Illustris. The goals were multifold. We wanted, first of all, to try to address some of the physical issues identified in Illustris galaxies and halos. We wanted to introduce new subject treatments for the feedback, new physics, and include numerical improvements in the code. And also we wanted to significantly expand upon the scope reached by Illustris, also by including new diagnostic tools. And practically speaking, this forced us to produce two new things. One is a new model, a new effective, or revised effective model for galaxy physics in cosmological simulations, and we are using the code AREPO, and a new set, a cool one, of cosmological simulations. I will talk about both today, but first I have, again, to get you some input, to give you some inputs about Illustris. So this is a very complex plot, but please follow what I'm saying. So in practice, Illustris was incredibly successful at reproducing the galaxy population. But when you then go and compare in details this galaxy population to observations, you may realize that something went wrong, and this is kind of obvious that it would have been the case. 6 things were most dramatic, and I just want to focus on 3 maybe. So if you plot the galaxy stellar mass function, so as a function of stellar mass, actually 0, the data and the simulation, the observational data and the simulations were not in agreement, and this happened both at the high and low mass end of the galaxy stellar mass function. If you, for example, picked a certain stellar mass bin, there was not in Illustris a very strong color bimodality as the one seen in SDSS. But maybe the most surprising result was that in Illustris, halos of 10 to the 13 or 10 to the 14 solar masses ended up being devoid of gas. There was not enough gas, redshift 0 within R500, within the Vira radius. You can see it here by comparing the solid curve with Illustris results to the data. And other few things. And we wanted to try to solve those, and I would like you to notice that all these problems were related in a way either to an inefficient star formation suppression, or generally speaking, to some inadequate feedback models. So we tackled the feedback in the new revised model, and in a nutshell, it's a bit long to describe the new model, but as I said, we started with the code AREPO and the whole Illustris framework. And just to remind you, we are solving gravity and the Euler equations, but then we also need a whole series of instructions to convert gas into stars, and then let the stellar population evolve and reach the interstellar medium and make feedback from the stars or from the black hole. So these are all what we would call semi-analytical models, in a sense, in our numerical models of the gas and the matter, stars, and black holes. So if you want to remember something about how TNG differs from Illustris, the main aspect is that TNG now includes MHD, so we can follow the evolution amplification of the magnetic fields from high redshift to redshift 0. We have a new black hole-driven wind for the black hole feedback, for the AGN feedback, and we refined the galactic wind feedback. Galactic wind is our way of doing the stellar feedback. And also we revised a series of choices on the stellar evolution, the yields for the metallicities, and also Repo now is equipped with some cool diagnostic tools. We can identify shocks in our gas. We can track the metals. We record now whether the metallicity came from supernova type 1a, type 2, or AGB stars. And we also have a subgrid prescription for neutron star mergers as possible site for europium. And if you want to remember something more about the differences in the black hole-driven wind and the feedback, just so both in Illustris and in TNG, we have two modes of feedback at higher accretion states and the lower accretion states, and we change just the lower accretion feedback, as I said, now is a kinetic kick of the gas immediately surrounding the black hole, while in Illustris it was a thermal dump in the intracluster medium. And if you want to remember something about the galactic winds, maybe you can go home with the idea that the TNG winds now are a lot faster at all mass scales and all redshifts. They are relatively more energetic at the low masses, and we now allow the energy of the winds to depend on some properties of the interstellar medium, like the metallicity. And incredibly, this model still produced galaxies that look like galaxies, and then telling you is not so obvious. So these are, for example, some random selection of the galaxies from the new model. But if you want to be more quantitatively, here I show you a series of observables that we always look and try to get right in our galaxy populations. So again, it's a busy plot, just a moment. So in every plot there are two curves. In red is Illustris outcome, in black is the outcome of the TNG model, and this is in we will call it a test box, already with hundreds and thousands of galaxies. But for the plot on the star formation rate density, all the curves are running averages, also for the galaxy mass function. So we have star formation rate density, the stellar to halo mass relation, the galaxy stellar mass function at redshift 0, the sizes of the galaxies, the content of the gas, and the black hole mass relation. And we managed to solve some of the issues we mentioned before and identified. So now we are able to form and grow smaller galaxies at the low mass end of the halo mass functions, as you, for example, can see here, or you can see here. And we also solve some of the problems at the high mass end, thanks to the new feedback in the AGN, where finally our 10 to the 13 halos have gas, for example, and also the stellar masses of the massive objects they seem to be going into the right direction. Let's put it like that. All right. All what I've shown you so far was thinking about the main body of the galaxies. So indeed, we try to choose our models based on the properties of the galaxies. But what about outside the galaxies? So here is a movie of the same 10 megaparsec box in Illustris model above and TNG, and you have gas density, gas temperature, gas metallicity, and the stars. I'm sorry you cannot see the redshift, but here we are more or less at redshift 2.5, and we are going down to redshift 0. And what I would like you to realize is that actually how we modify the intergalactic medium, first the circumgalactic medium and then the intergalactic medium in the two models is very different. So, and you can see here, for example, in the temperature, where in the Illustris model there were the bubbles of the old AGN feedback model, and we get very different topologies of the gaseous halo in a way. And you can see there's the difference becoming more and more dramatic towards redshift 0. So a movie like that, together with the plots I've shown you before, in practice is telling us two things. First, that we are really dealing with what we always say, a multi-scale, multi-physics process. And so, for example, suppose that the two models produce the same kind of Milky Ways. That doesn't say anything about how we are polluting the IGM with the two different models. And the other thing is that Well, we need cosmological volumes because, first of all, we need large volumes because we want a lot of galaxies. You cannot make a galaxy stellar mass function with 50 Zoom simulations. And also because we want to understand what the galaxies do to their surrounding material, to their surrounding volumes. So we wanted volumes, and these are. So these are the new simulations we have been running in the last year. So now we have 3 new cosmological volumes, all run with the same TNG model, all with updated cosmology, all including MHD. So we call, the name just tells you the size in megaparsec of the box. These are periodic boundary conditions. TNG 100 is the remake of the old Illustris, but with the revised galaxy physics models. And then we have a big box of 300 megaparsec on a side, and we are running now a 50 megaparsec on a side box. And the resolution of this box is the same as in Illustris. We are talking about, baryonic mass of 10 to the 6 solar masses. This is a factor of 8 worse, but this is a factor of 16 better. So with TNG 50, we are really going towards the direction of the Zoom simulations. And just to give you an idea of what you can do with these kind of simulations is, like, let's count the objects that we have. This is the matter projection, but if I was interested in studying galaxy clusters, you need at least a 300 megaparsec box. Here we have finally of the order of 200, 300 objects above 10 to the 14 compared to 10 in the old boxes. At the same time, we're starting to resolve Milky Way as well as in Zoom simulation, and here we will have the order of 100 Milky Way galaxies, Milky Way-like halos. All right, I just conclude by showing you, not this one, this one. I just show you the output, just to give you an idea of what comes out from our simulations. So here you have a projection of essentially the TNG 100 box. This is dark matter density projection. This is gas density projection, velocity of the dark matter actually. This is gas temperature where you can see the halos, and inside here there are all the small galaxies, right? This is, if you were looking at this box in X-ray from Bremsstrahlung, and this is the metallicity of the gas, which tells you about how we are polluting the gas surrounding galaxies and halos. This is a cool stuff. I mean, this is the ratio between the metallicity of the gas produced by supernova type 1a to the ones of HGB stars. Whatever, something new that we want to study. And this is, for example, the amplitude of the magnetic fields, which are amplified in high-density regions. I told you we have a shock finder. These are the Mach numbers, the projection of Mach numbers in our shocks. And this is, for example, the energy dissipated in our shocks, where you can see maybe here, where you can see both the shocks of filaments becoming filaments from the cosmological accretion, and also shocks from feedback, actually. So I hope I got your interest in this new set of simulations. Please stay tuned. We will have some cool results coming out about the galaxy color bimodality. You heard something about radio halos at the high mass end, and we can study anything we want. For example, also properties assembly of the intracluster light. And I'll stop here. Thanks. Absolutely.
And so one should not take that for granted. One should also not stop at the point of agreement, because with more physics you might be a disagreement.
Yeah, it's true.
So my question was related to this statement. So it wasn't clear to me, is the updated subgroup physics that you're doing based on better observations and understanding of those processes, or are they designed to fix the problems that you encounter in the previous simulations?
As you can see, it's a mix of the two, right? So we had some problems we needed to fix. But it's also true that there are winds observed around black holes, and we know that there are jets produced by black holes. We cannot possibly with this resolution model jets from the black holes, but we can model what we think that the jets are doing to the surrounding gas, kicking around the gas and heating it up by converting, So it's a mix of the two things. For example, the fact that we want to put B fields, magnetic fields, it's because we want to be able to address the phenomenology that is observed, and we couldn't do before.
I was going to say that even with this improved feedback, you were making the point that galaxies might look similar in the optical, but the certain galactic medium and the filaments look very different in terms of their temperature profile and atomicity. So along these lines, we've been actually running a project with a large group of people getting ready for the LINX mission to be able to directly image these certain galactic medium in X-rays and really get at the process of feedback. And so far we've been using Illustris, so maybe you could join and contribute the next generation.
No, of course. In a sense, what we are saying is that ultimately, to validate this model, we have to look at the whole environment in which galaxies are sitting. And indeed, it's not enough to just produce the right Milky Ways with the right stellar masses. Indeed, there's a lot of more.
And having multiple groups attacking the same problems is also useful to calibrate for people outside these groups, calibrate uncertainties.
Indeed, so we can look at the differences in the various predictions and not just match the problems that you already know you have, but also the reservoir that you're relying on to or just injecting.
I think it's just a matter of where you are tackling the problem from. I mean, we still want to make galaxies. And we want to make X-ray halos who host resolved satellite galaxies, possibly with the right colors and stuff like that.
Thank you very much. And we can move on.
All right. My name is Sihan Yuan. I'm a graduate student here working with Daniel Eisenstein. Today I'm going to talk about using galaxy pairs to investigate the three-point correlation function in the squeeze limit. Okay, so first we're going to talk about some basic concepts. The basic setup is that you have a dark matter overdensity field where the most overdense regions you will have dark matter halos, and you will have some galaxies living in these halos. The first point is that galaxies are biased dark matter tracers, and by doing statistics on galaxies, you can infer properties of dark matter. One statistic you can use on the galaxy distribution is the three-point correlation function, or 3PCF. It's usually given in zeta. It's proportional to the number of triangles with configuration R1, R2, R3. So if you look at this diagram here, R1, R2, R3 are the three sides of the triangle. And when one of the sides is much shorter than the other two sides, we call this a squeeze limit. That's when you have very tight, skinny triangles. Next important concept is the halo occupation distribution, or HOD. It's defined as the number of galaxies per halo as a function of halo mass and possibly other parameters. The HOD is important because it's probably the most popular framework to describe the galaxy-halo connection. And understanding constraining the galaxy-halo connection is one of the most important goals in cosmology. So for our talk, for this paper, we're going to use the HOD from Zhang 2009, which is fitted to SDSS luminous red galaxy data. Specifically, it's given number of centrals and number of satellites as a function of a halo mass. A central galaxy is defined as the most massive galaxy inside a halo, and the satellites are the other galaxies. As you can see, the centrals go from 0 to 1 as you go to very high halo mass, and the satellites go from 0 to infinity as a power law. Okay, so probably the most important idea of the talk is that closed galaxy pairs are objects too. We care about pairs because they trace the more massive halos than galaxies. Specifically, here we show a halo mass distribution of galaxies in red, and halo mass distribution of pairs in blue. And you can see pair halos are about 10 times more massive than galaxy halos. So we're going to do statistics on pairs. Specifically, we're going to do a cross correlation between the pairs and the galaxies. And we're going to use this cross-correlation to constrain the high mass end of the HOD. Okay, so with a pair-galaxy cross-correlation, you can define this quantity called a pair-galaxy bias. BPG is a function of pair separation. So if you look at this diagram, the two galaxies within the pair are separated by dp. The third galaxy is distance r away. BPG is defined as a fraction where the numerator has an integral of some weighting function times the pair-galaxy cross-correlation power spectrum. On the denominator, you have the same thing, except we have the galaxy-galaxy power spectrum. WK is some kind of weighting function defined in Fourier space that selects our large scale for R. This is because we want to keep the cross-correlation on the large scale, so we're calculating linear bias. So the important intuition here is that the pair-galaxy correlation is essentially a squeezed 3-point correlation function if R is much greater than dp. So if dp is much less than R, you have a very tight and squeezed triangle. Okay, so here is the BPG signal as a function of pair separation. So this is generated from simulation data. And the separation is divided into perpendicular to line of sight and parallel to line of sight. So immediately you see this very strong peak at about 2 megaparsec, where the pair galaxy bias is about 2, showing that the pairs are indeed very biased against the galaxies. So this peak is actually due to the fact that pairs with 2 megaparsec separation trace the most massive halos, thus they're the most biased. At larger separation, you see this very strong anisotropy. That's actually due to the filamentary structure of the universe. So specifically, when you select a pair that's mostly perpendicular to the line of sight, that means the local filament is also perpendicular to the line of sight. The weighting function that we have is set up in a way that is anisotropic, and it selects out space that's perpendicular to the line of sight to account for redshift space distortions. That's why when the pair is perpendicular to the line of sight, you get the most overlap between the pair and between the cross correlation and the weighting function, thus getting a strong signal. So this plot is to show you that this pair galaxy bias that we defined actually depends both on small scale effects such as the galaxy halo connection and large scale filamentary structure, which is very interesting. So now we're going to relate this pair galaxy bias to a squeezed 3-point function. Again, we have the definition of BPG. And after many pages of algebra, we can relate BPG to the general 3-point function zeta. So we choose to parameterize zeta by this coefficient QEF. QEF is defined as the general 3-point function zeta divided by a cyclic sum of 2-point functions. So each of these C is a 2-point function. Nice thing about QEF is that in the squeeze limit, QEF reduces to a function of only pair separation dp. This is because the cyclic sum divides out the large-scale dependence of zeta. Okay, so here are two plots showing QEF, the squeezed 3-point function coefficient, as a function of pair separation. Here you have in real space, and here you have a redshift space. So this is after incorporating redshift space distortions. So in real space, you see that QEF actually covers the same behavior as BPG, again showing that the squeezed 3-point function and the pair galaxy cross correlation is essentially the same statistic. In redshift space, however, you see that the 2 megaparsec peak gets blown out along the line of sight. This is because these most massive halos have high peculiar velocity, giving a very high virtual pair separation along the line of sight. So you see that at about 25 megaparsec separation along the line of sight, you get a very strong pair galaxy bias or 3-point function. The large scale anisotropy also gets smeared out, but you can see a little bit here. So how are we going to use this squeezed 3-point function or QEF? We're going to use it to constrain the HOD. Specifically, the thinking is that when you have an HOD, you can generate a galaxy distribution from an n-body simulation. And then from the galaxy distribution, you can calculate various statistics such as the 2-point correlation function and the 3-point correlation function in the squeeze limit. People have already thought about how to use the 2PCF to constrain the HOD, and we are going to try to use the squeezed 2PCF to offer extra information, extra constraints on HOD, specifically in the high mass regime. So to do that, we'd like to find different HOD prescriptions that have the same 2PCF, so that any variation we see in the squeezed 3PCF is unique to the 3-point function. It's not degenerate information in the 2PCF. This turns out to be hard, and so far we found two similar HOD prescriptions that are about 10% different in HOD parameter space, and 6% difference in the 2PCF, and 4% different in the squeeze 3PCF. Actually, just yesterday, we actually did better than this, but we're going to leave it at that. And we have not fully disentangled the squeeze 3PCF from the 2PCF, but we're optimistic because we have only explored a very small corner of the parameter space. And there are also more sophisticated HOD models, such as the ones that incorporate assembly bias, that we should explore. Okay, here is a summary. So we have used pair-galaxy cross correlation to compute the pair-galaxy bias and associate it with the squeeze 3-point function. We found that the QEF is a non-monotonic function of pair separation, revealing rich information on small-scale galaxy halo connection and large-scale filamentary structure. We've used these squeeze 3PCF to try to constrain the HOD, and we believe that this statistic can potentially break degeneracies in the 2PCF and further constrain the HOD. That's it. Thank you.
So within the standard implementation, the information content is so similar between the two statistics, that you should be able to then rule out or constrain modifications to the standard model, right? If the HOD depends on large-scale density or something, then it would probably be very different signals between the two statistics, right? The treatment function is sensitive to higher density regions. So
Yeah.
if HOD is dramatically different in that region of the universe.
Mm.
You see it preferentially in the three-point function.
Yeah.
It's a way to constrain the underlying assumptions in the halo optimization model.
Mm.
Which is a very good thing, because then Charlie can check whether his original paper on this
Yeah.
from more than a decade ago. Any other questions? Well, it looks like it was clear, and
I'm glad.
a very productive summer in September.
Thanks.
I want to make this clear. You're very welcome.